interested in maybe some kind of career in STEM, science, technology, engineering, medicine, math? Any of you interested in that kind of a career? One gentleman here. That's it? Just one person? Two?
I'm interested, but I don't know what I want to do yet.
Okay, well. Okay. All right. Just curious.
Yeah, I like it as a hobby. Yeah, it's interesting knowledge. Maybe
Yeah.
not a career.
Yeah. Well, you know, even if you don't pursue a career that involves science or technology or medicine, I would hope that you would at least have curiosity about the natural world and about some of the discoveries that scientists have made. And hopefully that you also recognize that these discoveries can actually be faith affirming. They can encourage you in your faith. So to recognize that God is revealed in nature and that science is uncovering details about nature should be motivation for all of us, I think, to spend some time becoming familiar with what's happening in the sciences. Because again, it's through that process that you see evidence for God's fingerprints. All right, so what I want to do again is continue in the exploring the design argument. And in this session, we're going to be giving emphasis to the watchmaker argument for God's existence, but we're going to talk about different versions of the watchmaker argument that we can advance, okay? All right, so before I do that, any questions from the last session, any comments, any points that you'd like to raise or elaborate on a little bit more before we go forward? All right. So this session is going to be focusing on DNA, but again, there's a larger design argument that can be made. And I don't know if any of you know who David Letterman is. Any of you know who David Letterman is? Right. So he had a late night show called Late Nights with David Letterman, I think was the name of the show. Right? Yeah, okay. Okay, so that's encouraging. I'm making a pop culture reference that you guys are aware of. I was a little concerned that I would be making pop culture references that nobody knew what I was talking about. But on the David Letterman show, every so often he would do the top 10, the list of top 10 things. You guys remember? I don't know if you ever saw that. Let's see if I can. The top 10 with David Letterman. It's kind of not the best image. So you can see David Letterman sort of behind there, right? So anyway, and this is meant to be kind of a humorous section of the late night show. But I took inspiration from this, and I want to talk about something actually pretty somber, which is what some people think to be the 10 greatest threats to the world that we live in. The 10 greatest threats. Now this is based on actually an article published in the USA Today, I think in 2017. So it's a little bit dated. But I think when you look at the list of threats, you probably are going to recognize that these are things that you probably are concerned with. So according to the USA Today, going from 10 to number 1, these are the 10 greatest threats in the world today. Fiscal crises in key economies. So the idea is that in 2008, there was the great financial crisis that impacted the world. And so the idea is if there are fiscal crises taking place in key economies in the world, that drags world economies down. Number 9, structurally high unemployment or underemployment. This isn't a problem, thankfully, in the US today, but in some parts of the world, unemployment is extremely high, and that leads to poverty, it leads to social unrest. And as we are looking to develop more and more technologies like AI, that begins to displace people from actually having careers that they can work at. So, water crisis. I live in Southern California, and we are in the midst of a drought, and there's not enough water, and there are too many people in the state. And this is now affecting most of the western part of the United States.
Not that there isn't ways to solve that.
What?
Just don't want to do it.
Well, there are ways to solve it. One is building desalination plants, which I think we're going to get to in the near future. Okay, severe income disparity. And this is a problem as the middle class disappears, right? This is a problem. Failure to mitigate climate change or to adapt to climate change. This is a really big concern, increasingly, that many people have. And let's see here. What are we at? 1, 2, 3, 4, 5. So this is number 4 on the list. Greater incidence of extreme weather events. Global governance failure. Food crises. And then failure of major financial mechanisms and institutions. So these are, again, some of the, and then finally, profound political and social instability. I miscounted. So anyway, this is just meant to be, I wouldn't say fun, but it's to introduce the idea that we live in a world where there are some pretty serious, significant threats that we are faced with that involve political instability, changes to economies, the failure of economies, the failure of financial institutions which provide the economic resources that are available to people to stimulate economic growth, climate change, and the list goes on and on. We could probably even add to this list the concerns about a future pandemic, given that we just went through COVID. But there is actually a pretty significant existential threat to our world that never makes these kind of lists, but it ought to. And that is what I want to talk about today in light of the design argument, and that is the digital data crisis. I don't know if any of you have heard of this, but this is actually a pretty serious problem. That we have currently over 44 trillion gigabytes of data that exist in the world that we have generated. And we continue to generate data at an increasing exponential rate. And that data has to be stored somewhere. And that amount of data would require 10 billion people, each person with 6,000 compact disks to hold that data, right? So that gives you an idea. If you think about what it would look like in your bedroom if you had 6,000 compact disks in the bedroom, right? And that's how many, again, compact disks you would have to have for 10 billion people, which is 3 billion more people than exist on the planet right now, in order to store all that data. The problem is that the media that we have to store data, magnetic tapes or hard disks, actually have a finite lifetime. And so that means we have to keep producing media storage devices in order to keep up with the growing demand. And the problem is we don't have enough high quality silicon on Earth to store all the data. So by 2040, the projections are we're simply not going to be able to store any more data. That we're generating, and data, again, is becoming very critical to many facets of our lives. The ability to store and retrieve and access data is very, very important. So this is actually a very serious problem that many people are concerned about. And so the question is, how do we solve this digital data storage crisis? And believe it or not, the answer to that problem is actually the DNA molecule. The DNA molecule. People believe that we can gain insight from DNA as well as utilize DNA as the next generation of data storage media in order to solve the digital data crisis. And this idea of turning to designs in biology or biochemistry to inspire solutions to engineering problems, to develop new technologies, is an area of engineering known as biomimetics and bioinspiration. And we mentioned that very briefly yesterday. And what I want to talk about is, again, how DNA is inspiring new technology. Technology like, again, the technology that would be used to solve the digital data storage crisis. And in fact, DNA is, again, such an elegantly designed, such an optimal molecule that it's inspiring not only new technologies to store digital data, it's actually inspiring a whole new type of computing called DNA computing, and it's even inspiring advances in nanoelectronics, where people are looking to build electronic devices at the molecular scale. And the reason why DNA is capable of doing this is because DNA's primary role inside the cell is to store information. DNA is you guys are probably familiar with the structure of DNA, right? It's this long chain-like molecule where there's actually two molecular chains that intertwine around each other, right, to form the double helix. And each chain is made from discrete molecules. There are 4 molecules that are called the genetic letters A, G, C, and T. And it's the sequence of those letters that contains information. Just like the sequence of letters in an alphabet can be used to form words. Words are information, right? Same thing with DNA. But because they're discrete units, it's essentially digital information. So DNA stores information that the cell needs to make itself and to regulate its operations, and that information is in the form of digital data, right? And in fact, DNA is optimized to store information. Some people believe that DNA is at the theoretical maximum in terms of its capacity to store information per unit material. In other words, there's no material that we know of that can store more information than DNA on a per unit basis, on a per weight basis. And I'm not going to go into the details of the structure of DNA and why it's so optimized, but in this book that I wrote, The Cell's Design, I talk about that. So if you really want to roll up your sleeves and get into that, this is maybe something you want to check out. Okay, so in what way is DNA affecting emerging nanotechnologies? Well, we mentioned, again, this idea of DNA being used as a digital data storage medium. And again, DNA is highly optimized to store data, to store information. In fact, people estimate that 1 gram of DNA can store 455 exabytes of data. That's 10 to the 18 bytes of data. In other words, 1 kilogram of DNA can store all the digital data that's in the world today. Okay, a kilogram in pounds is 2.25 pounds. So think about it. 2 pounds of DNA, a little over 2 pounds of DNA, can store all the data that exists in the world today. Compare that to 10 billion people with 6,000 compact disks apiece. Think about that. That's the difference in data storage capacity, which is absolutely remarkable. And because of that, people are looking at how they might go about using DNA as a digital storage medium. And in 2012, and since that time, people have done follow-up studies. So this is kind of the landmark study that was done by a guy named George Church, who's at Harvard University, and he and his team encoded an entire book in the DNA molecule. And this book consisted of 53,246 words. It had 11 images that were part of the book. JPEG images are digital images, and that's actually in 2 dimensions. And what they did is because DNA is a molecule and it can break down, they broke the DNA into fragments where each fragment corresponded to a page in the book. And then if you had multiple fragments, it meant that if one of the fragments broke down, you still would be able to retrieve the information in the book. And then they used little pieces of DNA sequences as locators that would help you find the fragment of DNA you're looking for. This would be equivalent to using page numbers in a book. Right? So, very interesting idea. But the point here is that this is pointing the way to, again, using DNA as a digital data storage medium. Now, one of the drawbacks is that it's very difficult to write the data to DNA and read the data from DNA. So people are trying to work on ways to simplify that process. And it may be that DNA's best use would be as a long-term storage device, for long-term storage, as opposed to a device that you would use to access data very frequently. But because of DNA's ability to store information, as people understand what it is about the DNA molecule that makes it work, that they are actually using DNA as an inspiration to try to design man-made polymers that would be more useful in terms of, again, a digital data storage medium inspired by DNA, but designed in such a way to allow for the more rapid access to that information. Now, that information in the cell is readily accessed because the cell has machinery specifically designed to do that very thing, but we don't have that machinery available to us. Okay, now there's another way that DNA is also inspiring new technology, and this is called DNA computing. And the idea here is that, again, DNA consists of digital information built into the molecule, right? And that information is accessed by the cell's machinery. That information is read, and then in some cases that information is used to replicate the DNA molecule. It replicates. This is critical for cell division. It also is copied in the form of a molecule called messenger RNA that then that goes to the ribosome where proteins are made. And then there's also pathways that can repair DNA. If DNA gets damaged, right, that information is corrupted. And the way you overcome that corruption is identify the damage and then repair it. So DNA has a mechanism to repair any damage to itself. These are all basically computer operations, where the cell's machinery is manipulating the digital information in DNA in the same way that computer systems manipulate digital information. And to understand this, and this to me is one of those things that when I think about this, it just keeps me awake at night. This is just so mind-blowing. But to think about this, we need to think about something known as DNA computers. Are any of you familiar with Alan Turing? Do you know who he is? Some of you do, right? He's considered by many people to be the father of computer science, modern-day computer science. And Alan Turing, prior to World War II, laid out the theoretical foundation that led to the invention of modern-day computers. And as it turns out, Turing actually built the very first computer system before anybody realized what he had done in service to the cause of the Allies in World War II. The Germans had something known as the Enigma code, which is how they would communicate. They would communicate using this Enigma code. And Alan Turing and a team of mathematicians were charged with cracking the Enigma code. And Turing actually did that, and the way he did it was actually through building the very first computer system that was based on his theoretical work. And this was all classified information that when it was declassified, people realized that Alan Turing was a war hero. That people believed that his work at cracking the German Enigma code actually shortened World War II by about 2 to 3 years, saving, by some estimates, over 15 million people's lives. So anyway, a war hero, but his ideas are very simple from a theoretical standpoint. He envisioned these these theoretical machines that he called Turing machines that consist of three components: an input, an output, and a finite control. So here's a cartoon of a Turing machine. Right? This is, again, just a cartoon. So you've got digital data going in, a stream of ones and zeros, right? And that digital data that's going in is operated on by some kind of abstract machine called a finite control. And that finite control operates according to a set of rules that will alter that digital information as it goes in, producing an output. And Turing's genius was to realize that the input of one machine could become the output of another machine, right? And that you could string together Turing machines with different finite controls, and by doing that, you could actually achieve pretty complex operations, right? By just simply combining these Turing machines together. Now, these are all theoretical machines that existed in Turing's mind, right? That were written down on paper that allowed people this theoretical framework that they could then use to build computers, to build actual computers. Well, it turns out that computer scientists have discovered that if you think about DNA, again, as digital information, and you look at the different molecules that are involved in the process of DNA replication, which is a very elaborate process, where one DNA molecule is replicated into two daughter molecules, that there's a whole host of proteins that are involved in this process. And these proteins are basically Turing machines. They're taking digital input in DNA that go into that enzyme that alters it, producing a digital output in the form of DNA that then is operated on by another molecule, again, another Turing machine, and by combining the operation of all these Turing machines together, you can affect essentially DNA replication. This is basically a computer operation. This is literally a computer operation. Here is a video that shows, again, this is a computer simulation that shows the machinery that is involved in DNA replication. So this is a simulation looking at the replication of DNA. And remember that the DNA is like this strings of data going in and going out. And look at this. This is literally, again, a collection of Turing machines. And this is literally a computer operation. But again, look at the machine-like nature of what's going on there. That literally is a computer operation. In fact, the similarity between computer operations and what DNA is doing in the cell, what the cell machinery is doing to manipulate DNA is so stark, that similarity is so stark, that actually has inspired this new area of nanotechnology called DNA computing, where people are literally building computers using DNA and the enzymes or the proteins that manipulate DNA in the cell. And these computers are stored in these little test tubes that are about this big. These are called Eppendorf test tubes. They're about that big. And they are more powerful than the most powerful supercomputer system that has ever been built. That there are problems that DNA computers can solve that supercomputer systems that we've built can't solve. They're that powerful. And there's technical reasons for that. But this is Leonard Adleman. He's considered the father of DNA computing. And this is what this is, again, the advantages of DNA computers. There's massive parallelism in the operations. The capacity to store data, as we mentioned already, is enormous. And they are highly energy efficient. They operate at near theoretical energy efficiency. And again, they can solve problems that silicon-based computers can't solve. This is another technology that DNA is inspiring. And these are called DNA wires. And this is a little bit technical. It's really cool, but it's a little bit technical. It turns out that you can actually conduct electrical current along the length of a DNA double helix. that if you attach a chemical group to one end and another chemical group at another end, you can blast this group with this chemical compound with light. That will eject an electron from the chemical compound. It flows through the DNA double helix, the interior, and it will chemically react with that compound at the other end. It literally is functioning as a wire. And it turns out that this is actually used as a way to recognize damage in DNA in the cell. And so you have these proteins that bind to the DNA, and these proteins have these metal centers that can send electrons back and forth along the DNA. And these molecules will hop on and hop off depending on whether they've given up or received an electron. But if there's damage to the DNA, it's like you're breaking the wire, the current can't flow, and the cell recognizes damage and then is able to find that damage and to repair it. So the point is that this is inspiring the invention of nanowires, where people are using DNA as wires in these nanoelectronic devices. So can you imagine building electronic devices at a molecular scale that are made up of DNA? So in other words, the point here is that DNA is such this remarkable molecule. It's so efficient, so optimized in terms of its capacity to store data, to store digital data, that it's inspiring at least 3 different technologies: data storage technology, DNA computing, and nanoelectronics. And not only is DNA inspiring new technologies with biomimetics and bioinspiration, but we can use these kind of advances to make a case for the creator. And this is all, again, based on the watchmaker argument. So here's, again, the argument that we mentioned earlier. This is an argument developed by William Paley in his book, Natural Theology. And this is how Paley describes the watchmaker argument. In crossing a heath, you know what a heath is? It's like a meadow. Heath is a meadow. In crossing a heath, suppose I pitched my foot against a stone and were asked how that stone came to be there. I might possibly answer that for anything I knew, to the contrary, it had lain there forever. But suppose I found a watch upon the ground, and it should be inquired how the watch happened to be in that place. I should hardly think the answer which I gave before, or which I had before given, that for anything I knew, the watch might have always been there. Yet why should not this answer serve for the watch as well as for the stone? Why is it not as admissible in the second case as in the first? For this reason and for no other, that when we come to inspect the watch, we perceive what we could not discover in the stone, that it has several parts that are framed together for a purpose, that they are so formed and adjusted to produce motion, and that motion so regulated as to point out the hour of the day, that if the different parts had been differently shaped from what they are, or placed after any other manner or in any other order than that in which they are placed, either no motion at all would have been carried on in the machine, or that none which would have answered the use that is now served by it. This mechanism being observed, the inference we think is inevitable, that the watch must have had a maker, that there must have existed at some time and at some place or other an artificer or artificers who formed it for the purpose which we find it actually to answer, who comprehended its construction and designed its use. So that's essentially the watchmaker argument, that there's certain features that, again, that a watch has that reflect the work of a watchmaker. And then Paley argued that when we look at biological systems, these have more in common with a watch than they do with a rock, and therefore if a watch requires a watchmaker, then life must require a creator. And so we can actually now take this type of reasoning and look at what people have done with the DNA molecule and actually develop, again, 3 different variations of the watchmaker argument. One of them is what we'll call a revitalized watchmaker argument. This argument of William Paley has been largely dismissed over the years. People claim, well, Hume's critique undermined the logic of the argument, and that Darwin suggested ways in which design could appear in nature without the work of a creator. But I would argue that the advances that are happening in biochemistry help us to revitalize the argument. And one way this argument is revitalized, again, is to note the eerie similarity between biochemical designs and human designs. And we talked about molecular machines the last hour. Well, now we can talk about DNA computers. That, again, the operations in the cell that manipulate DNA are literally computer operations. So Adelman said this: the most important thing about DNA computing is that it shows that DNA molecules can do what we normally think only computers can do. This implies that computer science and biology are closely related, that every living thing can be thought to be computing something, and that sometimes we can understand living things better by looking at them as computers. Notice the statement in light of the watchmaker argument, right? It's essentially a watchmaker argument that's being presented. Now, another variation of the watchmaker argument would be what we could call the watchmaker prediction. The watchmaker prediction. And this is something that I proposed in my book, The Cell's Design. And this is what the prediction involves. As human designers develop new technologies, examples of these technologies which previously went unrecognized will become evident in the operation of the cell's molecular systems. In other words, if the watchmaker analogy truly serves as evidence for the creator's existence, then it is reasonable to expect that life's biochemical machinery anticipates human technological advances. All right? Do you guys get what I'm driving at there? In other words, when we think about the watchmaker argument, what we're doing is we're saying, here's a technology that we invented, and we see similarities to that technology in the operation of the cell. That's the watchmaker argument. But then we can make a prediction that if indeed the cell's chemistry is the work of a designer, as we invent new technologies, what we would predict is that examples of that new technology would exist inside the cell. And where this watchmaker prediction becomes satisfied is with, for example, the recognition that DNA serves as a wire. I can remember when Jacqueline Barton at Caltech made the discovery of DNA wires. At that time, people thought that this was a really interesting idea that could be used for technology purposes, but they questioned whether it had any relevance to what was happening inside the cell. So here's a new technology that was invented, namely DNA nanowires. And it turns out that about a decade later, she and her team actually discovered that the DNA wire effect is a very important physiological property of DNA. In other words, this is a fulfilled prediction of the watchmaker prediction. That here's a new technology, we would predict that we would see evidence of that technology in the cell, and lo and behold, we do. And there's other examples that I could cite. So in other words, this is another way that we could argue for the watchmaker argument. This is a variation of it. Does that make any sense to you guys? And then lastly is the converse watchmaker argument. Now, what Paley was doing again was he was looking at human designs, and then he was saying those human designs have similarity in biological systems. Therefore, that's evidence for a creator. But we could go the other direction too. We could say, well, if the designs in biology are the work of a creator, then they should inspire new technologies. This would be what I would call the converse watchmaker argument. If biological designs are the work of a creator, then these systems should be so well designed that they can serve as engineering models and otherwise inspire the development of new technologies. And this actually is not only another variation of the watchmaker argument, It actually allows us to respond to what I would call the blind watchmaker challenge. Right? Are you guys familiar with the idea of the blind watchmaker? Right.
Evolution, right?
Yeah, yes. This is the idea that the design that we see in biology is not the work of a watchmaker, but is the work of evolution, which is the blind watchmaker. So Richard Dawkins, in his book, The Blind Watchmaker, said this: Paley had a proper reverence for the complexity of the living world, and he saw that it demands a very special kind of explanation. The only thing he got wrong was the explanation itself. The true explanation had to wait for Charles Darwin. Natural selection, the blind, unconscious, automatic process, which we now know is the explanation for the existence and apparently purposeful form of all life, has no purpose in mind. It has no mind and no mind's eye. It does not plan for the future. It has no vision, no foresight, no sight at all. If it can be said to play the role of a watchmaker in nature, it is the blind watchmaker. Right? The problem here is that
How can something unpurposeful invent something purposeful? That's basically what you just said.
yes, Dawkins defines biology as the study of complicated things that have the appearance of being designed for a purpose. So he would argue that it doesn't actually produce systems with purpose. It produces systems with the appearance of purpose. It's not true purpose, but it appears to have purpose. Right? So in other words, that purpose is something we impose on the system. It's not something that actually exists in a purposeful way. Right? So that's right. So there's, no part of evolutionary theory is there's no ultimate design or purpose or directionality or intentionality behind the process. Now, this idea of biomimetics and bioinspiration, though, challenges the blind watchmaker claims. So, again, the fact that, DNA, which is emblematic of a lot of biological and biochemical systems, that it inspires new engineering advances, new technologies, challenges the blind watchmaker idea. And this is the reason why I say that. So that not only can it inspire, different versions of the watchmaker argument, it also inspires a response to the challenge, to the main challenge to the watchmaker argument. And the idea here is that evolutionary processes are unguided, undirected, they're blind. They have no directionality. This is how people conceive the process. They co-opt existing designs and cobble them together into new designs. So in other words, evolutionary biologists say that evolution works on what's available. And if these are the biological systems that are available, evolution will basically use those systems and modify them into new systems. But the point is that this process does not produce optimal, well-designed systems. It produces systems that are inherently suboptimal and inherently flawed. Ken Miller says this: evolution does not produce perfection. The fact that every intermediate stage in the development of an organ must confer selective advantage means that the simplest and most elegant design for an organ cannot always be produced by evolution. In fact, the hallmark of evolution is the modification of pre-existing structures. An evolved organism, in short, should show telltale signs of this modification. But the point here is that evolution doesn't produce optimal, perfect systems. Okay, now let's think about that for a minute. Evolution produces kludge jobs, right? So now let's think about this for a minute. If this is what evolution produces, then why would anybody in their right mind turn to biological designs to inspire new technology? Right? Why would anybody do that? That makes no sense. Now, it might be possible that on rare occasion that happens, but to have an entire academic and industrial discipline called biomimetics and bioinspiration built on copying the designs in biology suggests that the designs in biology are not imperfections. They're elegant systems. They're elegant, sophisticated designs that are far beyond what we could achieve on our own as human designers. That's exactly the type of system that I would expect that a creator would produce, right? And this goes back to the passage in Job that I mentioned yesterday, if you recall, that ask the animals and they will teach you, or the birds in the sky and they will tell you, or speak to the earth and it will teach you, or let the fish in the sea inform you. Which of all these does not know that the hand of the Lord has done this? So the point is that this idea of the watchmaker argument is something that a lot of apologists actually shy away from, in my experience. And they shy away from it because the argument has been criticized over the centuries for its logical problems, for the fact that evolutionary mechanisms can account for that design. But in reality, the watchmaker argument is a very powerful argument that is being given new life thanks to our understanding of biochemistry and the use of biochemistry to inspire new technology. And so this allows us to bring to bear variations of the watchmaker argument in fresh new ways. And what I like about the argument is, again, similar to the argument from beauty, is that in my experience, most people understand the watchmaker argument. It's not like some versions of the cosmological argument for God's existence or the ontological argument for God's existence, which I don't understand at all. I just can't understand that argument. The point is, you don't have to be sophisticated to use the argument. You don't have to be sophisticated to understand the argument. It's an accessible argument, is my point, right? You know, if you talk to people about motors and machines, they have a concept of what that is. And then if you're able to show them that there are these motors and machines that are in the cell, they immediately recognize the point. Or people know that computers come from intelligent agents, right? And so if we see computer systems at the core of biochemical systems, this again is an accessible argument, right? So there's power in the watchmaker argument, is my point. There's power in the watchmaker argument. Any questions, comments? Okay.
That made a lot of sense. The last statement about how that why would you duplicate something that was imperfect for perfection?
Right. If I was an engineer and I needed to solve a problem and I had to stake my livelihood and my career on solving that problem, I wouldn't turn to designs that were flawed, right? Okay, well, let's take a break, and then why don't we come back at a few minutes, let's say 5 after 11. That gives us 15 minutes.
I have a question.
Yes.
So at the beginning of your talk, you were talking about